October night in 1944, German Oberschütze Wilhelm Müller adjusts his position within the battered remains of a farmhouse on the Eastern Front, his fingers dancing across the unfamiliar apparatus strapped to his back as his breath forms ghostly clouds in the frigid air. The weight of the equipment, nearly 25 kilograms of batteries, transformer and power supply, presses against his spine as he peers through the specialized ZG-12 Vampire infrared scope mounted atop his modified STG-44 assault rifle. Through the greenish haze of the scope's image, he can discern the outlines of Soviet infantry advancing cautiously through the darkness 200 meters away, completely unaware they are being observed. The enemy's soldiers, confident in the protection offered by the night, move without the caution daylight would demand. Müller's finger tightens on the trigger as the crosshairs settle on the lead figure. The rifle cracks, its muzzle flash momentarily illuminating the ruined building. But to his targets, death arrives invisibly from an unseen assailant who can breach the ancient sanctuary of darkness. This moment marks one of the earliest deployments of the Nachtjäger Night Hunter system that would earn the nickname Vampire for its ability to see in darkness and for the distinctive infrared backpack system that seemed to drain the life from its bearers through physical exhaustion. The device represented the culmination of years of secret German infrared technology development, a desperate innovation introduced in the final stages of a war already lost, yet it would forever change the nature of night warfare and cast a long technological shadow into the Cold War and beyond. The development of the Vampire system began in earnest in 1943, when German military planners, confronting the increasing effectiveness of Allied bombing campaigns and the gradual loss of air superiority, recognized an urgent need to exploit any remaining technological advantages. German scientific research had established an early lead in infrared technology, building on foundational work by physicists like Robert Richard Pohl at Göttingen University, who had experimented extensively with lead sulfide photocells capable of detecting infrared radiation. The Reich Research Council, under the direction of Abraham Esau and later Hermann Göring himself, prioritized the development of night vision capabilities as part of the broader Kammhuber Line air defense network. Initial efforts focused on vehicle-mounted systems for tank and aircraft operations, with the first functional prototypes emerging from the laboratories of AEG Leitz and Zeiss by early 1942. These early systems, designated FG-1250, were bulky affairs requiring substantial power supplies and offering limited range and resolution, but they demonstrated the fundamental viability of passive night vision technology at a time when Allied forces primarily relied on active infrared searchlights that revealed the position of the user. The critical breakthrough came in August 1943 when a team led by Dr. Hans Schumann at the Leitz Optical Works in Wetzlar successfully miniaturized the infrared converter tube sufficiently to permit mounting on personal weapons. The core of the innovation lay in the photocathode, a zinc oxide cesium compound applied to a thin curved glass plate that would emit electrons when struck by infrared radiation. These electrons were then accelerated across a vacuum chamber and struck a phosphor screen, creating a visible greenish image of sufficient brightness and resolution to permit accurate targeting at ranges up to 250 meters under ideal conditions. The resulting ZG-1250 scope, when paired with a specially designed infrared illuminator designated Vampire, represented a quantum leap in night fighting capability. The system was engineered for integration with the revolutionary Sturmgewehr 44, the world's first true assault rifle, creating a combined weapons platform that could deliver accurate automatic fire in complete darkness, a capability unprecedented in warfare to that point and offering a potential tactical advantage that German high command was desperate to exploit despite the system's considerable limitations and the increasingly dire strategic situation facing the Reich. The fundamental challenge facing the German designers centered on power requirements for the infrared illuminator and image converter tube. Unlike modern passive night vision devices that amplify ambient light, the Vampire system required an active infrared source, essentially an infrared searchlight invisible to the naked eye but detectable by the specialized scope. This illuminator demanded substantial electrical current, initially requiring a vehicular power source until the development of the specialized EG-1224 backpack power unit. This cumbersome apparatus consisted of two 6-volt lead-acid batteries connected in series to provide 12 volts of direct current, which was then converted by a mechanical vibrator unit to the alternating current required by the transformer. The transformer stepped up the voltage to the 1,500 volts necessary for operating the image converter tube. The entire assembly weighed 13.5 kilograms for the battery pack alone, with an additional 6.2 kilograms for the converter, connecting cables and supporting frame, imposing a significant burden on soldiers already carrying standard combat loads. Battery life presented another critical limitation, offering only 30 to 40 minutes of continuous operation before requiring replacement or recharging, a severe tactical constraint that necessitated careful deployment of Vampire-equipped soldiers for maximum impact during critical phases of night operations rather than extended use. Despite these substantial drawbacks, the system offered something previously unattainable: the ability to engage targets accurately in complete darkness at ranges exceeding what was possible with traditional night fighting techniques. The Vampire system's deployment to combat units began in March 1944, with initial field tests conducted by specialized Nachtjäger companies attached to SS Panzergrenadier units on the Eastern Front. The first operational deployment involved approximately 310 complete systems distributed to selected Waffen-SS formations, including elements of the 4th SS Panzergrenadier Division Polizei and the 3rd SS Panzer Division Totenkopf. Each Nachtjäger team typically consisted of the primary shooter carrying the Vampire-equipped STG-44, a battery carrier responsible for the power backpack, and 2 additional soldiers providing security and carrying spare batteries. The specialized nature of the equipment required extensive training, with dedicated courses established at the infantry school in Doberitz, where selected personnel underwent intensive 2-week programs covering the operation, maintenance, and tactical employment of the system. Technical challenges abounded in field use. The sensitive electronics proved vulnerable to moisture and extreme temperatures. The infrared illuminator's limited range required operators to close with enemy positions more than was often tactically prudent, and the distinctive infrared signature, while invisible to the naked eye, could be detected by enemy forces equipped with similar technology, potentially revealing the operator's position to specially equipped counter-sniper teams. Despite these limitations, after-action reports from commanders indicated that Vampire-equipped units achieved surprising success in night ambushes and defensive actions, with documented engagements showing significantly higher hit probabilities compared to conventional night fighting techniques, particularly in the confused close-quarters combat characteristic of the Eastern Front's forest and urban environments. The manufacturing process for the Vampire system represented a remarkable achievement under increasingly difficult wartime conditions. Primary production was distributed across multiple facilities to reduce vulnerability to Allied bombing, with Leitz's Wetzlar plant producing the optical components, DG facilities in Berlin manufacturing the electronic elements, and final assembly taking place at underground facilities in the Harz Mountains. Production figures remain disputed by historians, but surviving Wehrmacht quartermaster records indicate approximately 3 to 10 complete systems delivered to frontline units, with perhaps another 600 in various stages of completion when Germany surrendered in May 1945. The manufacturing process required extraordinary precision, particularly for the photo-cathode components, which needed specialized vacuum deposition equipment and highly skilled technicians. The cesium compounds used in the photocathode were extremely sensitive to contamination, requiring clean room conditions that became increasingly difficult to maintain as Allied bombing intensified and critical. Resources became scarce. Each ZG-1229 scope required approximately 47 man-hours to produce, with the associated EG-1224 power pack requiring an additional 28 man-hours, making the complete system one of the most labor-intensive infantry weapons in the German arsenal. The unit cost, estimated at 2,800 Reichsmarks per complete system, represented nearly 14 times the production cost of a standard STG-44 rifle, a level of resource commitment that reflected the desperate German search for technological force multipliers as their numerical disadvantages grew increasingly insurmountable in the war's final stages. The technical specifications of the Vampire system revealed both the ingenuity of its designers and the practical limitations imposed by 1940s technology. The ZG-1229 scope measured 30.5 centimeters in length, 12.7 centimeters in height, and weighed 2.25 kilograms. The objective lens featured a 60 millimeters diameter with specially formulated glass that maximized transmission in the near-infrared spectrum while filtering visible light. The image converter tube achieved a resolution of approximately 80 lines per millimeter at the center of the field, degrading to 60 lines per millimeter at the edges, providing a recognizable human-sized target at ranges up to 250 meters under optimal conditions with strong infrared illumination. The infrared illuminator incorporated a specialized filter that blocked visible light while transmitting approximately 85% of radiation in the 700 and 900 nanometer wavelength range. The system provided a field of view of 8.5 degrees, considerably narrower than modern night vision devices, creating a tunneling effect that required operators to move slowly and deliberately to maintain situational awareness. The EG-1224 power pack utilized two 6V20AA lead-acid batteries connected in series, measuring 44.5 centimeters in height, 31.8 centimeters in width, and 17.8 centimeters in depth. The mechanical vibrator converter operated at approximately 300 cycles per second, generating significant heat and a distinctive high-pitched whine that experienced Soviet troops eventually learned to recognize, somewhat diminishing the system's stealth advantages in static positions. Despite these limitations, the Vampire represented the most advanced man-portable night vision system fielded by any combatant during World War II, offering German forces a significant tactical advantage in the specific conditions where the technology could be effectively deployed. The operational impact of the Vampire system has been subject to considerable post-war debate among military historians. While German after-action reports claimed extraordinary success rates, with some Nachtjäger units reporting kill ratios exceeding 3.1 in night operations, these accounts must be viewed with appropriate skepticism, given the propagandistic tendencies of late-war German military reporting. More reliable Soviet accounts from the Eastern Front do confirm encountering German night fighters with special equipment that could see in darkness, particularly during defensive actions in East Prussia and Hungary during the winter of 1944-45. Red Army veterans described the psychological impact of taking casualties from invisible assailants during night operations previously considered relatively safe, forcing changes to Soviet infantry tactics in the final months of the European conflict. American forces encountered Vampire-equipped units less frequently, though documented cases exist from the Ardennes offensive in December 1944 and the defense of the Rhine crossings in March 1945. A captured Vampire system was extensively evaluated by U.S. Ordnance Corps personnel at Aberdeen Proving Ground in mid-1945, with testing confirming both the system's technological sophistication and its practical limitations. The evaluation report concluded that while the Vampire represented an impressive technological achievement, its weight, limited battery life, and restricted field of view rendered it of limited tactical value, except in specific defensive scenarios. This assessment, while technically accurate, perhaps understates the psychological impact of night vision technology on opposing forces and its influence on post-war military research and development priorities. The intelligence race to secure German infrared technology accelerated dramatically in the final months of the war as Allied forces advanced into German territory. Soviet SMERSH and American ALSOS teams specifically targeted research facilities and production centers associated with the Vampire program. The Light's optical works in Wetzlar fell into American hands largely intact, providing significant documentation and prototypes, while Soviet forces captured several key AEG engineers from the Berlin facilities before they could be evacuated westward. The subsequent exploitation of this technology proceeded along parallel tracks in the emerging Cold War environment, with both superpowers incorporating elements of German design into their own first-generation night vision systems. The American T3 carbine infrared night sight, first fielded during the Korean War, demonstrated clear technical lineage to the ZG-1229, though with significant improvements in battery life and weight reduction. Similarly, the Soviet Nu-2 system, first observed during Hungarian operations in 1956, incorporated principles derived from captured Vampire technology. Perhaps more significantly, German infrared research accelerated Western understanding of semiconductor properties of materials like lead sulfide and indium antimonide, contributing directly to the development of infrared detection technology, with applications ranging from heat-seeking missiles to thermal imaging systems for civilian applications, including firefighting and search and rescue operations. The technological legacy of the Vampire system thus extended far beyond its limited wartime deployment, influencing military and civilian technological development for decades after its creators had been defeated. The tactical employment of vampire-equipped units reflected German late-war doctrine, emphasizing the concentration of specialized capabilities at critical points, rather than broad distribution. Typical deployment patterns involved positioning Nachtjäger teams at likely avenues of enemy night approach or infiltration, particularly covering gaps between defensive positions that could not be effectively observed using conventional methods. The distinctive capabilities of the vampire system were particularly valuable in forest and urban environments, where traditional flare illumination proved inconsistent and often provided more advantage to attackers than defenders by revealing defensive positions. German tactical manuals emphasized strict fire discipline for vampire operators, recommending engagement only when targets presented clear, high-value opportunities, both to conserve battery life and to prevent premature revelation of Nachtjäger positions. The limited deployment of the system prevented its incorporation into broader German night fighting doctrine, but surviving combat reports indicate that when properly employed by well-trained operators, vampire-equipped units could effectively disrupt enemy night operations out of proportion to their numerical strength. One particularly notable engagement occurred during the Soviet Vistula-Oder offensive in January 1945, when a section of vampire-equipped grenadiers from the Großdeutschland division reportedly ambushed and destroyed a Soviet reconnaissance company attempting a night crossing of the Pilika River, demonstrating how the technology could temporarily restore the advantage to outnumbered defenders, even at this late stage in the conflict when German forces were facing overwhelming numerical disadvantages on all fronts. The technological legacy of the vampire system extends well beyond its limited operational impact during World War II. The fundamental concept of converting infrared radiation to visible light through an electronic image converter established the foundation for night vision technology that would evolve through multiple generations in subsequent decades. The first-generation passive starlight scopes that became ubiquitous during the Vietnam War represented direct evolutionary descendants of the vampire, though with critical improvements, including ambient light amplification, that eliminated the need for active infrared illumination. The principles pioneered in the vampire's power supply and optical systems influenced not only military technology, but also contributed to civilian applications ranging from astronomical observation to medical imaging. Perhaps most significantly, the vampire system demonstrated the potential for technological asymmetry to provide tactical advantages even in the face of strategic defeat, a lesson not lost on military planners during the Cold War and beyond. Modern night vision capabilities, from the advanced helmet-mounted systems used by Special Operations Forces to the thermal imaging technologies that enable precision strikes in complete darkness, all trace their conceptual lineage to the hastily developed backpack-powered system that first allowed German soldiers to violate the ancient sanctuary of darkness in the final desperate months of the Third Reich.